redrawing this picture that we've seen a few times this morning of the, I guess, original, more or less, TFNP classes with these reductions between them. So you've seen definitions of most of these, and I'm also going to draw this class CLS, which is, well, so these classes have been studied for a while and contain various natural problems. And I guess 10 or 15 years ago, well, that's the older class. This is the newer one defined by Daskalakis and Papadimitriou. Continuous local optimization. I won't say much about the definition, but there were lots of things about games and so on that were known to be in PPAD and in PPLS, so in their intersection. So they defined some kind of natural problem that these things also fit inside. And then it was open for a while whether this actually equals the intersection of these two classes. And it was shown a little bit ago by Fearnley and others that this class CLS actually does equal the intersection of PPAD and PLS. So it's a natural question then, are there other intersections that hold that we could find? Now there is one which I guess we deliberately didn't look at, which lives here, which is this class SOPL, which kind of comes from proof complexity and lives at the intersection of these things. But let's pretend we don't know about that for this talk. So otherwise, in these older classes, our result is that there's no other intersection. That say if you look at these, we were trying for a while maybe to show that PPAD is the intersection of these two, but it's not. The reason one might think there's some intersection happening here comes partly from these proof complexity characterizations. So this PPA corresponds to, in the way that Robert was saying, it's null cell and sats over the two-element field, which I'll just write as NS2. And this PPAD is this unary null cell and sats over the integers. Yes, please tell me if I should write bigger or talk more slowly. And then this is this unary Shirelli Adams. And let me draw some other classes here, actually. So we could call this PPA2, as this is to do with parities. And one can also define PPA3, more or less as the things arising from the three-element field. And other primes, and in fact composites, but let's stick with primes. So these are known to be separate. And if you look at this, one can sort of imagine how, if you had a proof over the two-element field, would there be some way to, maybe if you have one over here and one over here as well, is there some way to get it down to here, possibly using extra assumptions from here? But we'll show you can't do things like this, that there's no two classes which give a third one of the intersection apart from this. And the reason for this is feasible disjunction, which I'll write the definition of in a minute. But there's a kind of rule of thumb that says that a TFNP class is an intersection. So I'm not saying this is true, but this is a useful way to think about it. If and only if its proof system does not have feasible disjunction. So the results I want to talk about are failure of things being intersections based on known feasible disjunction results on the one hand, and also that the proof system for this actually does not have feasible disjunction, based more or less on the fact that it is an intersection of classes or an intersection of proof systems. But we don't have any general result of this form, but it's a useful guideline.
Excuse me, Neil, so this is a theorem or a rule of thumb?
It's a rule of thumb, it's not a theorem, probably not true. So what is feasible disjunction? So definition. So we take F and G, C and F formulas in disjoint variables. And suppose that, unfortunately, I'm going to write it as a conjunction. F and G has a small refutation in some system P. So these are usually defined with refutational systems. So the name feasible disjunction comes from thinking about proofs of disjunctions, but I'm going to write it in terms of refutations of conjunctions. So you've got to mentally negate everything and change disjunction to conjunction. So suppose you're in this situation, then the feasible disjunction property or FTP says that either F has a small refutation in P or D does. So just to say it once in terms of disjunctions, this says that if there's small P proofs of F or G, then there's either a small P proof of F or a small P proof of G. And if F and G have disjoint variables, this is what you'd expect to be true, because how does having the other thing floating around help you prove one or the other? Really, one would expect this to hold, and it does hold, but not for everything. Yes, and what is this word small? So there's different meanings of feasible disjunction depending on what you mean by small. And actually, there's also some other meanings depending on whether you can find things in polynomial time, which I won't go into. But small for us is going to mean low degree. Well, the original definition is about size. So that's one possibility of small. Also low degree. Also this combination of size and degree that Robert was talking about. So examples might be North-Stellensatz over any field has the feasible disjunction property or degree. And this is observed in this paper on separation by Mika and Robert and so on. And I'll say something about why this is true. Shirali-Adams has the feasible disjunction property for log of magnitude plus degree. So this is something we show, and here this is a version of this measure of log of size, but the magnitude is just sort of the absolute value of the biggest coefficient that occurs in the proof. And I guess the result also is that these funny proof systems, reversible resolution and reversible resolution with terminals, they do not have this property of size. Right, so this is going to tell you something about PPAD and these PPAs, because that's Null-Stellensatz kind of systems. This is something about PPADS, because that's unary Shirali atoms. If we had unary Shirali atoms here, and we had log of size plus degree, we would get some fairly precise correspondence with PPADS. The way that this measure here, small proofs in this measure is not quite the same thing, because we don't, we're over the rationals rather than the integers. So this is one way in which this sort of fails to be true, or that's more like a heuristic, in that we prove some of these results using feasible disjunction, not quite for the corresponding system, but for something close enough that we can use it. And these things correspond to CLS and SOPL, which I didn't write, which are intersections. So you can show they fail feasible disjunction.
So what is reversible resolution with D?
So reversible resolution is what Robert, I think, finds. So it's resolution, but it's made somehow more algebraic by some restrictions on it. And T is with terminals, and it's an extra condition, which I'm not going to say. But it's a system that corresponds to CLS.
Oh, okay.
So let me briefly say how you get some of these feasible disjunction results, and then say how you can get at least one of these non-intersection results out of it. So feasible disjunction property for Null-Stellensatz, third degree. So there's a let's say proposition due to Bass from 98, that if you have a system of polynomials Q, then it has no NS refutation of degree D, where this is a result that holds for any field, if and only if there is a D design called big D, the Q. And this is a simpler version of what Noah was just saying about pseudo expectations. So a D design is a linear map E from, if this is our field, then it's from all polynomials to, well, let's say F again, which looks like it looks like an assignment that satisfies Q. Setting Q to 0. So every polynomial in Q more or less gets set to 0. And if you multiply two polynomials, the D of them also gets multiplied. So sort of as long as you only look at low degree polynomials, doing this to a polynomial resembles evaluating it on an assignment that makes Q 0. And then it's fairly simple to get feasible disjunction from this. So we have a fact. Let DQ and DR be designs for systems Q, and this is in variables X, and a system R, so in variables Y. Sorry, by system here I mean system of polynomials, so maybe it arises from translating this here. So we have two systems of polynomials, Q and R, in disjoint variables. We have a design that looks like it satisfies Q, and it's a design that looks like it satisfies R. Then there's D designs. then their product, composed with DG, is the design for the conjunction, or for the union of these systems of polynomials.
You mean DQ and DR?
Yes, sorry. So what is the product? We can think of these as linear maps that really are defined on monomials. So given any, if you have any monomial that might occur, say, in a refutation of this in Null-Salazar. So we'll have some x variables and some y variables. You just write it as a product of a monomial x and monomial ny. You apply d to the x parts and dq to the x parts and dr to the y parts, and you get some number. And then it's straightforward to show this behaves like a design. So this implies that the result I've said, this FPP for Null-Salazar with respect to degree. So what is the reason for this? It's that I guess going back to F and G. So, well, suppose Q together with R has. Yeah, so the result is the kind of contrapositive of this. It says that the fact that these have D designs is like saying both of these require degree at least D in Stonebacks. And so this result says that both require to be D, then the union also requires degree D. We're now in the improving the union, we're allowed to mix variables together. But this says that the lower bound carries over. So that's the contrapositive of the feasible disjunction problem.
Could I ask, why do you have to do things sort of dually? Why can you not just write things primarily? So Null-Salazar certificate will be writing one as a combination of polynomials from F. You have, so if you have a low degree certificate, why can you not just set the variables of, because they're in disjoint variables, why can you not just set the other variables to 0 and get a certificate for F?
I don't know, I haven't tried that. I assume it turns into a mess, but I don't know.
So I'm saying that, can you not just prove this fact item directly without going to designs? I just say, because if you combine F and G and they have a low degree certificate, right? Then you just, let's say that so you have two things. You have F is an X's, G's and Y's, right? So then if you have a low degree certificate that uses both X's and Y's, just set Y's to 0, and then you get a low certificate for F.
Well, no, the axioms from the second.
Well, the problem is that you can't just set them to 0 because they're unsatisfiable.
No,
I'm
saying that this just happens over a field, right? So now these are polynomials over a field, so you can set variables.
So I don't know, it might work, but let's talk about it
Okay,
later.
so
I think what you do is you substitute the values given by the design.
Yeah, exactly.
That's it, yeah. So this is a simple version of this, and this is going to tell us something about things below these PPAs. And so one result in the paper, though, is showing a similar result for this Schreier with respect to magnitude. So this is by extending some things in Thomas Hakaniemi's thesis. He has a very similar result for sum of squares, and we can kind of get it for Schreier. So we get the other feasible disjunction. So I have 5 minutes to prove the main result, which is just an example of one of these intersection results. So we'll suppose, for a contradiction, that we do have some class. So let's take an easy one. Is this PPAD equals the intersection of PPADS with PPA. So one consequence of this would be that PPADS intersect PPA is contained inside PPA 3, the thing on the right, And the reason I'm moving to this is because we have a simpler feasible disjunction property here, which I just. So we know that we have these search problems that are complete for these classes. So there is a system of a sequence of CNFs, for example, for this single line principle. It doesn't really matter what we use actually, which is complete for such that the search problem, as Robert said, is complete for PPADS. And for PPA 2, we know that this count 2 modular counting CNF, which I won't define, is complete for PPA. And then if you just take the search problem for the conjunction of them then, so Fn and count 2, this is in the intersection. There's a search problem here that says, given an assignment, find a false clause here or a false clause here. So we know that using PPADS, we could find a false clause here. Using PPA, we could find a false clause here. So it's in both classes, so it's in the intersection, which implies that it's contained inside PPA 3. And now we can use the feasible disjunction for null ansatz. So let me finish quickly. So I guess actually I should have written here. So this implies that this thing has low degree refutations in null ansatz over the 3-element field. By this characterization of PPA3 as things as corresponding to this proof system. And then by a feasible disjunction property for NF3, either, so one of these must have low degree refutations. For each n, one of them has a low degree refutation. So either one or all large n, this principle Fn, which was complete for PPADS, has low degree in null ansatz. But if this is true, then by the correspondence, we have that PPADS is contained inside PPA3, which we know is false because of proof complexity bounds. The other option is for infinitely many. So for infinitely many n, the other thing, this count 2 principle, has low degree in NF3. And this also contradicts some of the proof complexity bound. So this just contradicts the fact that you can't do these modular different primes. So that's more or less the trick that's used in all these cases, finding some suitable proof system with feasible tablet.
What about the possibility that it's a intersection of PPADS and all the PPAK?
We did not rule that out. I mean, with all the intersection of all of them gets a bit dodgily defined because you include just standard primes or non-standard primes. So there's a lot of questions you could ask there, but
there are these usual theorems that, like in field theory, if it's true for all positive characteristics, something's true in characteristic 0, you'd almost but those are sort of model theoretic type things.
yeah, there's a result. Well, so you have this these low bounds for counting principles that tells you that all these PPA classes are separate. And I think there's a paper with authors I don't remember that shows that even if you take kind of PPA modulo P, where P is a prime of size log n rather than being a fixed thing, at the intersection of all these, then you can still use this counting argument to get something separate. So, but you could define an even bigger intersection, and then I'm not quite sure what would happen. But at least once you start doing that, it doesn't go to this other thing immediately.
Thank you, speaker.